Haixia. I'm from Nagoya University in Japan. Today I'm very excited to present our research at this 40th anniversary of MOND. Our journey will take us from the challenge of missing mass problem to a novel approach with the gene sequence as discriminators. First of all, the mystery begins when we notice that something unusual in our galaxy. This rotation curves does not behave like the Newtonian dynamics suggested they should. It was as if a vast amount of mass, unseen and unknown, was influencing these stars and gas. This issue became as known the missing mass problem. To reconcile this, different theories emerged. The most popular one is dark matter, suggests the existence of some invisible particles. But another significant theory is MOND, suggesting a modification in the Newtonian's law at low accelerations. Such alternative theories also include MOND and QMOND. But however, until now, no observational test is conclusive for these two competing paradigms on galactic scales. And one of the most compelling evidence of MOND is the observed relations between mass discrepancy and acceleration. In MOND, there is a strong correlation between these two, which is not expected in the dark matter paradigm. As we dive deeper into the galaxy dynamics, we have the gene equation. These equations describe the motion of stars within the galaxy, taking into account their velocity disappearance and the gravitational potential. However, here is the challenge. The gene equation alongside the Poisson equation gives us more unknown functions than available equations, rendering the system is not closed. A traditional approach to this issue makes some simplifications for closure. Typically, a distribution function is assumed for those two intervals of motion. By doing so, the corresponding velocities per terms in the gene sequence are reduced, and the gene sequence are closed. But these simplifications come with their limitations. As we all know, for decades, the sigma r and sigma d, representing the radial and vertical velocity dispersions, are not equal in the observed these galaxies. And also the sigma rz, which represents the correlation between radial and vertical velocities, is not zero. And furthermore, there is some increasing evidence supporting that the stellar orbits respect a certain interval of motion. And here's just an example, because this certain interval of motion makes an analytic expression, which brings additional challenge to this already complex problem. Now, these challenges bring us to our current research. We propose use the complete form of gene sequences as discriminators to distinguish between the dark matter and MOND. We don't make any simplifications as previous works did. First of all, since the mass models are axiometric, so we have these two mixed components of velocity spring tensor are zero. Thus, we can write these complete gene equations into two independent equations in the symmetrical coordinates. And here we can say only if theory does not need to put any additional assumptions to be consistent with the gene equation and observation, then this theory is correct. Thus, we define the two quantities, TR and TZ here, associated with the observed quantities and the acceleration. For our analysis, we use this fiducial mass model prescribed by MOND 2022. It was fitted from the data of Gaia DR2 and MDAR, the latest constraints we can get at the time. For the data tracers, we turn to the work of MOND 2020. they collect the kinematic data from a large sample of red cloud giants using the Gaia DR2 and LAMOST. These datasets give us a good coverage of the galactic disk, especially in the vertical direction. But we should note here, our sample is mainly contributed by thin disk stars, which are identified by their chemical properties. In this study, we will investigate these 4 models, and here we treat MOND as a gravitational potential model rather than a theory. In this work, it is applied in the style of low phantom dark matter plus the low baryonic, where the low phantom dark matter acts like an alternative to the popular dark matter halos, but reflecting the MOND effect. First of all, we make the traditional compare between the rotation curves and predictions. As expected, the Newtonian baryoniccontent model underpredicts the rotation curve. Dark matter and MOND match the data well within the 1 sigma arrow, and the mode systematically smaller than most of the data points. The key task of this research is the gene sequence test, namely the TR and TZ test, to examine how well the gravitational models agree with the data outside the galactic plane. First of all, we look at this radial direction. The TR monotonically decreases with R, which just reflects the trend of decreasing magnitude of radial acceleration along the radial direction. But on the mode side, the Newtonian model falls below the observed radial acceleration for all the locations. The fiducial dark matter model mostly lies within the confidence interval for the entire range, but except for at a low altitude, z equals 0.4 kilopascal. At this altitude, it falls outside the confidence interval for nearly the whole range of radius. But here, the MOND model performs the best, only for this TR test. For the TZ test, which evaluates the observed vertical acceleration, we find that all the 4 models are broadly consistent with the observations within the central confidence interval. However, the MOND performs, its performance here is a little bit mixed. It lies within the 95% confidence interval, only at higher altitude, but in the low altitude, in the left panel, MOND falls outside the confidence interval. So, when testing our models using the gene sequence, we notice that the Newtonian model and MOND don't fit the observations very well. They are clearly do not pass the test. And we note that when comparing the TZ to TR, TZ seems to have weaker discriminating power. This is because the smaller vertical potential gradients in these galaxies and the larger relative errors in TZ. For the dataset we use here, the relative errors of TZ are about twice as large as of those TRs, which affects the observed vertical and radial accelerations. And consequently, the error bars of TZ are significantly larger than those of TR at the same locations. So we still need to be conservative in our comparisons. The test depends on the tracer's density profile we adopt, and it's important to note that it doesn't necessarily discriminate for sure between the dark matter and MOND. And okay, as stated above, the major challenge of this work is that we lack of the knowledge of the shape of density profile of the tracer population, and we have to represent it by using the profiles of the general population in the galactic disk, such as the weighted geometrical thin plus thick disk model. However, this approach presents some challenges. First is the uncertainty about whether the red cloud giant follows the spatial distribution of giant stars. And second is the uncertainty about the degree of agreement between the chemically classified thin disk red cloud giants and the dynamically best-fitted thin disk of our fiducial model. To address these challenges, we also employed the alternative possible density profiles for the tracers in our test. And it has been done for both TR and TZ. By varying the tracer's density profile, we observed dramatic difference in the TZ result, while the TR result remains very stable. This suggests that the TZ are highly sensitive to the tracer's density profile. In contrast, the TR test appears to be relatively insensitive, and this makes them more robust in analysis. When we employ a thin disk profiles in the scheme of TZ test, as shown in the middle panel, we find that all the 4 gravitational models falls outside the confidence interval for almost all the spatial locations. This suggests that the actual density profile for our tracers is likely closer to a thin disk one. However, as I mentioned before, we should note that this sample is mainly composed by thin disk red cloud giants. Therefore, the result of the thin disk profile don't necessarily rule out any of the 4 gravitational models. Instead, this outcome highlights again the sensitivity of TZ test to the tracer's density profile. And when examining the effect of tracer's density profile and TR, we find that the dependence is not negligible. This reminds us to account for the uncertainties caused by the tracer's density profile if we use the r-directional density equation to calculate some quantities. And on the other hand, TZ's sensitivity to the tracer's density profile could be turned into an advantage. If we are able to constrain other quantities like the gravitational potential and the velocity squared, we can use these sensitive TZ measures to place tight constraints on the spatial distribution of a specific population of stars. So now our convergence results shows that the fiducial dark matter model and Q-MOND generally agree with the TR and TZ data. However, we find the systematic trends at low Z locations that pose concerns for both dark matter and Q-MOND. To delve deeper into these issues at low Z locations, we further examine the TR and TZ test as a function of D at 3 different positions of 7, 8, and 9 kilopascal. When analyzing the TR plots, we noticed that the radial field strength of the fiducial dark matter model consistently lies outside the central confidence interval, and notably, this trend of inconsistency with TR becomes worse as the R increases. And when we turn to the TZ plots, we observe a different trend. Here, the vertical strengths of the fiducial dark matter model consistently lie within the confidence interval, but the TZ of Q-MOND appears to lie slightly outside the confidence interval at lower altitudes, and this trend of inconsistency seems to lessen as the R increases. So this reminds us the question about the shape of the galactic dark matter halo, whether it's oblate, spherical, or prolate. Our analysis of potential at low altitude suggests that the real galactic gravitational potential, especially in its inner region, might lie somewhere between the fiducial dark matter model with a spherical halo and the phantom dark matter halo of Q-MOND. And this is, in dark matter terms, could be imply an oblate halo. However, we must remember that at low altitude, the extent of dark matter and Q-mount deviating from data depend on the tracer's population and its density profile, the choice of tracers, samples, and the frequent process of the spatial distribution of these queries could also include some bias. So therefore, at this point, we consider this question as still open for the further investigation. In our current research, we have used the sample of red giants from as tracers. We divide these stars into thin and thick disk populations, but we haven't performed a detailed classification or fit the density profiles. So for some future work, to minimize the bias from the choice of tracers, we will make use of the data of Gaia DR2 combined with the LAMOST DR8. We will further divide the white cap giants into subpopulations based on their chemical properties and carefully design and test the functional form of the tracer's density profile with different sets of parameters of each subsample. For the perspective of dark matter, the vertical dynamics can be explained if the shape of the dark matter halo is oblate for Milky Way. However, it could not need to be as extreme as the effective halo given by the Q-mount. Thank you. And recalling the early names of dark matter problems, such as missing, hidden, and extra mass, we also explored extra mass or extra gravity here. We first explored the difference in gravitational potential predicted by 3 models and compared with the Newtonian case. Also, we explored the corresponding gradients of the potential difference, namely the vector difference in the field strength. So at first glance, the magnitude of MOND extra potential is 1.5 times of Q-mount or dark matter 1. The magnitude of extra gravity in MOND is instead smaller than those two, which is in fact consistent with the systematic smallness of MOND in the rotation curve test. And just as expected, the extra potential of fiducial dark matter halo is spherically symmetric. On the other hand, the Q-mount provides an extra potential that is comparable in magnitude to dark matter, but the shape of the extra potential is quite flattened in the d direction. In other words, it suggests an oblate halo. So now the left panel illustrates the effective phantom dark matter density distribution of Q-mount. We can see the density distribution of Q-mount, phantom dark matter, shares more similarities with conventional spherical dark matter halo plus a disk-shaped component. Now we can say the phantom dark matter halo seems to provide too much gravitational accelerations in the vertical direction. This result leads us to probe deeper into the fluid dynamics. It set the stage for us to question whether the MDAR and therefore the modifying internal dynamics can represent the real gravitational potential in the real Milky Way. And so this is the last part. After decades of search, the dark matter particles have not been found. But today, our current research has reinforced the effective equivalence between dark matter and MOND at galactic scales. This apparent correlation between MOND and dark matter could be a beacon towards a new synthesis, one not reconciling and transcending both MOND and dark matter. And in the meanwhile, we can say that MOND could be a very good equivalent replacement for dark matter halos when you are doing some practical research and you don't need to manage in various preconditions and fine-tuning complex parameters. So that's a summary. Thank you.
people are still thinking about it, so I have one. So in his talks, thesis showed a model for the baryonic mass distribution in the Milky Way that is obtained by essentially imposing the RAR on the H1 rotation curve of the Milky Way, and therefore one can get the surface, the density profile of the baryons, including the bumps and wiggles that can be important in MOND, because you have to go beyond just a pure exponential disk. If there are structures, they have to be taken into account. So I was wondering whether, in your opinion, this may help, especially for the low Z discrepancy, that if you have a more realistic baryonic model, would ease the tension.
Actually, I think under our direction, the rotation curve test and the TR test is kind of same to each other, but on the vertical direction, I don't know if you have a more relativistic model will help there, because we also have another test a long time ago with the Nagoya 2017, and the conclusion is the same with this one. We use different models and we test with different data sets. Before that, we used the data from Wave, and now we are using Gaia DR2, and the models are also built from different observations. So, but the conclusion is the same. So I don't think the model can improve that.
Okay. Any other question? Yes.
I'm a bit confused at the fact that the MOND model seems to fail or to be a bit of a poor fit at very small distances from the galactic center, interior to 4 kiloparsecs. Interior to 4 kiloparsecs, there's not going to be, I mean, you're in a high acceleration regime, so I'm surprised there is much of a difference between the Q-MOND and the Newtonian prediction, the interior to 4 kiloparsecs, honestly. You're almost just a little beyond the bulge, so what's the accelerations there are going to be very high. I'm surprised there is a significant difference between Q-MOND and Newton in that region.
What you say is, yeah, I agree with that. In the center of the galaxy, the acceleration is high, so the MOND40 is not very significant. But the MOND is predicting the whole distribution of the potential in the galaxy. I think it matters if we look inside the galaxy. And since we have the data to test here, and we cannot say MOND field in the inner part, but it shows a slightly over prediction. So that's why we are thinking about maybe this comes from the tracer's choice. This result is influenced by the radical giant, and since it's very close to the center of the galaxy, we actually don't have much data there. So the arrow bars here is also very large. There is a very complex reasons behind this. So I cannot make a very strong conclusion that say MOND field. It's also an objective we will investigate further.
For example, a test of whether the whole thing works or not would be to go all the way out to the center, no? And if you have a strong discrepancy between the MOND prediction and the data within the bulge, then obviously there's something wrong about the MOND prediction and the way it's been implemented, no? Because within the bulge it should be exactly identical to the Newtonian prediction, pretty much. So if you see a difference between the Newtonian and the MONDian prediction towards the inside of the galaxy, that surely is alerting you to the fact that the distribution of tracers is off, or something is a little off. No?
Yeah, that's right.
Other questions? Yes?
Hi, thanks very much for that talk. And looking at the model, initial model you put in for the Milky Way, you said, yeah. On the baryon side, I meant. On the baryon side, you mentioned this paper. I think you referred to my paper about the double power law.
Yes, yes.
Yeah.
Okay.
But I'm more interested to know the part which you said about the interstellar medium disks, because Xu-Fen Wu, who worked with me in her thesis, we tried to model the interstellar medium part in multiple components. It's a numerical, it's an empirical model, not a beautiful set of formula, but it's did you include that?
So we use here H1 disk plus H2 disk. It's two components, but we didn't fit it because we just simply borrowed this model from the 1 and 2.
I remember our interstellar medium disk model was pretty complicated. Because that matters in predicting your vertical acceleration. Can matter whether we're in a bubble or not. That kind of things.
Also, you mean is that the substructure?
We actually didn't really put in this substructure in there, but those were axisymmetric models. I just suggest you to have a look at the Wu and and I think we also did. I think that paper was also done with Bename from Strasbourg, and have a look, see if we're actually comparing the same set of models for the math. That's it. Thank you.
Thank you.